In this video, we would like to present our work on heuristic-free optimization of force-controlled robot search strategies in stochastic environments. When manipulating objects in service or industrial robotics applications, the poses or features of the environment, such as holes, or features of the manipulated objects, such as pins, can vary stochastically between executions. Search strategies such as the probe search seen in this video can provide much-needed robustness, but inherently sacrifice cycle time to perform the search. In this paper, we try and find an optimizer to produce search strategies which optimally trade off robustness and cycle time. We built on prior work on program parameter optimization. Shadow program inversion is a heuristic-free black box robot program optimizer, but it is not data efficient or capable of handling non-stationarity. We propose to apply sequential transfer learning to shadow program inversion. For a given robot program, we first pre-train the shadow model on a large simulated training dataset. A training task is defined by a probability distribution over features of the environment. The pre-training dataset then contains a large number of training tasks. Each training task contains 128 training examples drawn from that task's probability distribution. We then fine-tune the shadow program on one test task representing a real environment. This dramatically reduces the number of real-world training examples. We then run shadow program inversion and execute the program with the optimized parameters on the real robot. By adding the resulting data to the test task dataset and fine-tuning again, we can close the loop and keep our program inputs updated even in the face of non-stationary processes. We evaluate our approach on 3 use cases, the first being spiral search for mechanical assembly. We generate a large pre-training dataset of 1,000 training tasks, each containing 128 spiral searches in that task's stochastic environment. We also collect 6 fine-tuning tasks, each corresponding to a different hole distribution, and had a robot conduct 128 spiral searches for each distribution. We compare against several baselines. The genetic algorithm did not converge quickly enough and produced a suboptimal search pattern. A handcrafted heuristic produced good patterns but relied on heuristics. TSBI produced an optimal pattern, covering the complete hole distribution while avoiding excess search in case of failure. Overall, we achieve failure rates very close to the handcrafted heuristic and considerably reduce cycle times in real-world settings compared to the naive and genetic algorithm baselines. We performed a similar set of experiments for probe search in the context of THT electronics assembly. We first generated 1,000 simulated stochastic environments and collected a large pre-training dataset. We then collected 128 probe searches for each of 6 real-world fine-tuning tasks. Again, TSBI is competitive with a handcrafted task-specific heuristic, while outperforming both naive and sophisticated baselines. Here we see that both the probability of success as well as the average cycle time are considerably improved without requiring any heuristics. We conducted an additional set of experiments involving probe search in simulated non-stationary environments. For stochastic drift, Brownian motion, and shift processes, continuous fine-tuning allows the optimizer to keep the program parameters, here the search pattern, up to date with the changing underlying probability distributions. In the last experiment, we compared our sequential transfer learning scheme to several first and second order meta-learning approaches and found that we outperformed them for both predicting the expected trajectory as well as the probability of success.